Okay, now we're going to move down south and have Michael Breakspear talk about neuronal models of dynamic functional connectivity, and he's going to also talk about linking different scales and data modalities. So,
okay, thank you. And really grateful for Raphael for organising this, and Maria, and delighted to be here. So my take is going to be somewhat different from the other talks we heard this morning. Here's the overview of my talk, basically in 4 parts. Most of us are imaging scientists, and I did applied maths, so I'm going to walk through some of the basic tenets of dynamic systems theory. Because when we're talking about dynamics or time-varying systems, we're really ultimately seeking to understand what is happening at the sort of core heart of the system of interest, not merely the statistical patterns that we see in the data. And that's going to be the sort of overarching framework that I bring to this session. A few talks on dynamic models of large-scale brain activity. What are they? How do we make them? Then 2 toolboxes that I'll just briefly overview, and then a bit of an applied session ending with this lovely-looking image from a postdoc in my group. Okay. So here's the historical example that I like to use. So they say Einstein discovered the universe. So what did cosmologists and physicists actually set out to understand was the motion of the celestial bodies. You know, this is one of the earliest observations of humankind, is looking up at the stars and seeing things move around, and scientists then setting out to discover the laws that underlie those movements. So here was a smart dude, probably way smarter than all of us, Ptolemy. He was a Greek guy. These are etchings. There's no photographs available from several hundred years ago, or thousands. And I doubt that he really walked around followed by his followers, but that's how he's perceived. And he's got a device and he's looking up at the sky, right? And he's using technology, which is better than just sort of lying on your camp bed looking up at the sky. So it's a great step forward. And using his observations and also mathematics, which is a recurring theme of mine, he came up with this self-consistent heuristic of the motion of the celestial bodies. Okay, but of course this was one with the Earth at the centre, and now we know he was wrong. Now, how do we... Not everybody actually still believes that he was wrong. In fact, some people apparently still believe the Earth is flat, but I've only got 35 minutes, so that's a segue. The reason we know or think he's wrong is really interesting. So, right, he had, the school had the Earth, and then they had the spheres, and that didn't quite work because the planets seemed to do this sort of thing. So then they had spheres upon spheres, and every time they made more careful observations, their model got more complex. And so model complexity versus model goodness of fit, they could make their models continue to fit the data by making them more complex. And this is a theme that's really at the heart of even what we do today, is this trade-off between model complexity and goodness of fit. So then some more smart dudes wearing these outrageous costumes and wigs that I think we should go back to. Copernicus, Galileo and Newton. They had a better technology. They had this imaging device called a telescope. But most importantly, 2 things also came along by then. One was a theory of optics. So this was a theory of how these measurements were made. And of course, if I go out at the opening ceremony tonight and I have a few drinks and I walk along, I can see the moon following me. So that's an egocentric interpretation of the universe, right? But now with the theory of optics and perspective and distance, I know that the moon isn't following me. Although if I continue to imbibe, maybe I'll go back to the original worldview. And the other thing, of course, Newton and Leibniz came up with calculus, the calculus. So dv dt basically is f divided by mass, the second derivative in space. And, of course, Newton had to develop this whole branch of mathematics in order to do that. And now we know with the sun at the centre, he was kind of more or less right. Classical mechanics lived for hundreds of years. And it's not quite right, of course, because Einstein came along. Now, what about us? Here we are putting people into scanners and looking at these lovely maps of the brain. But we're not making direct observations, just like the telescope. Our telescope is the MRI machine, or the EEG, or the MEG. And with MRI, our theory of optics is this observation of neurovascular effects. And Timothy will speak after Jessica and I about the fact that this is not necessarily just a passive measurement tool, but can be coupled to changes in brain states. You know, when you get aroused, I went and drank some coffee after getting off the plane this morning. I got aroused, and then all my hemodynamics change. So what we're going to do, hopefully following in the footprints of giants, is to have a bit of calculus here and then go from our observations to a theory of the brain. And I better hurry up. If we have a forward model, we can have a prediction. So we're going now from observations to predictions. We then do our measurements and come up with our observations. And just like Ptolemy, we get an observation error. And then we can make our models more complex to minimise the observation error. But then we must bear in mind, like there could be a Copernicus who comes up with a simpler model that has just as good fit. So this is this trade-off between minimising prediction error whilst also minimising model complexity. We can change the forward model, and the same model should then explain MEG data. So just with F equals MA, at the heart of this particular approach is this differential equation. X, these are the states, these are the neuronal states, membrane potentials, firing rates, synaptic conductances, and these are the inputs. They can be sensory inputs, they can also be fluctuations, random fluctuations. So what's happened since Newton is we've gone from ordinary differential equations for the smooth movement of the celestial bodies to random differential equations where we have smoothness and we have roughness. So this is stochastic calculus. This equation incorporates local circuit processes. You'll see many of these models in the literature now, but usually there's pyramidal cells, inhibitory cells, and connections between them. And then, of course, introducing the connectome, interactions between regions that are distant. And there you go. That's the recipe for basically all large-scale dynamic network models of the brain. Okay, brain network dynamics. So how do we understand? In a few minutes, we've talked about earlier PCA, k-means clustering. What are the similar technical linguistic tools in this framework? So this is the slide. So this is a vector, right? This is not just a scalar. So just pretend it's got two states. And then this is a vector field. So at each point, this function says where you're going next. It's just the derivative. And so we can look across all possible points in this so-called phase space, and we get what's called a vector field. And then we could start joining these with orbits, and then doing some calculus following a famous French mathematician, Poincaré, we find these beautiful things called attractors. So we've got vectors, vector fields, flows, attractors. That's the linguistic corpus of dynamic systems theory. So here's a attractor, and these correspond to the time series. So this is 3 dimensions now. You see this one's static, and these are periodic. If I change the parameters of my system, then we get what's called a bifurcation from a simple oscillation or a fixed point up to a more complex periodic orbit here. This is bursting. This would be like a 3 Hertz burst in the thalamus that you see during sleep. And if I change the parameters again, even if we've just got 3 dimensions and completely deterministic equations, we get this random aperiodic chaos here. Okay, so that's the notion of an attractor. Now, when you go to the literature of dynamic functional connectivity, you see many different terms flying around: metastability, multistability, metastates, criticality. Fortunately, in math, we can define each of these very precisely. So here's multistability. This is when our landscape would have more than one attractor. You might have a fixed point and a limit cycle coexisting at the same time. And if you put a bit of noise in your random differential equation, you can jump from one to the other. And this is what is shown here schematically. And I think this is what Vince was probably talking about with his different states. And then you can look at the dwell time, not just the mean dwell time, but the dwell time distribution. How often does the system get trapped in each of these states? You can have something called metastability, where the fixed points or the what we call invariant sets of the system aren't really attractive. So you go into them and then you go out of them, even without noise. It's like that Escher drawing with the ladders always going around and around. This is what metastability looks like, and it has a completely different dwell time distribution. And then criticality is basically when you've got an attractor but you get near it and it's so weakly attracting, you put a bit of noise in the system and then you just move around a little bit like a Brownian motion. And pretty much this is the complete dynamic repertoire of dynamics of what might be causing dynamic functional connectivity in the brain. Okay, so dynamic models of large-scale brain activity. Hopefully you've got a flavour and there's books and papers that you can read more about of what's going on here. We're talking about dynamics in the neural population that are then projected into what we observe empirically. How do we make a neural mass? How do we make a model of relevance to what we're doing in the brain mapping community? Of course, we can do these very sophisticated, detailed, what's called multi-compartment spiking models. This is what the Human Brain Project is doing. Remember, this is like the largest neuroscience project ever, so it's quite important. They're modelling every single compartment of every single neuron, and eventually they'll model a small patch of the rat barrel cortex, I guess. But it's not really going to scale up to the brain, at least not likely in our time frame. And the other problem with these models is they become very complex, right? How do you assess the goodness of the model when it's got billions of parameters? So what you can do is reduce each neuron to a simple spiking neural model. There's simulations for these, and you can wire them up according to known neurophysiology. Or you can just say, I don't really care about individual neurons, I just care about the mean activity of neurons. I'm not going to possibly model every single neuron, not in my lifetime anyway. So this is a mean field approach, and there's neural mass models that actually came from the 60s and 70s. And this process of going from detail to abstraction is a mean field dimension reduction. And it's no different from coming into this room and feeling the temperature. You know Boyle's law, what is it? Pressure equals volume times temperature, I don't know. Just got off an aeroplane. That's well established. So why not use it in neuroscience? And that's what we're having a go at. There is another principle. It's not just an epiphenomenon. In Australia, it's prohibited to publish a poll during voting day because then you can influence the way people vote. Oh, look, the bad guys are going up and I was going to do a protest vote, so I won't do that anymore. We know where that leads. But neurons do. They do feel the collective vote, if you like. And so this is a way of neurons getting trapped into the behaviour of the collective. Okay, so this is my favourite neural mass model. It's got 3 parameters: membrane potential for pyramidal cells and their potassium channel conductances, and membrane potentials for inhibitory cells. These two are very much like a grossly reduced Hodgkin-Huxley model. It's called the Morris-Lacar model, and basically sodium channels, calcium channels open and close much more quickly than potassium channels, which are slow, and you only need to model them and you can get something that looks like a spiking neuron. You add in a slow inhibitory population, and what's important is that you no longer have neurons go and spike. You replace that with a Gaussian over the population threshold, and you get these smooth sigmoid activation functions. And that's kind of how we get to a mean field approach here. So we can plug these in. To be honest, I did this when I was a wee young lad doing my PhD, or this was a few years after that, and there's a couple of dodgy terms, but anyway, it does behave brain-like. So here it is in a bursting state. This is a complex periodic attractor going around the surface of the torus, and here are the characteristics bursting behaviours that you see in many parts of the brain. And then I change my parameters. I say I'm going to increase the gain. Max Shine and I have been looking at that. And then we go to something called a chaotic attractor. This is my favourite attractor in all of dynamic systems theory because we've flogged it like a dead horse. There's a fixed point here which is unstable, and then the dynamics go up here and then they come down, and you get something like this. Deterministic aperiodic dynamics. Okay, so then you take that as a model of a patch of cortex. It could be a microcircuit, it could be a larger region, and you introduce these models, hundreds of them in different patches, and then you influence them through, allow them to couple. So the pyramidal cells in one region send their axons not just locally but down to through other parts of the brain to other regions with some time delay. So now we've got stochastic delay differential equations, and then you see what happens. Okay, so I'll come to what happens in a minute, but how do we see what happens, right? How do we go doing stochastic time delay differential equations? So this is part of the change that's happened in the last 5 years, that a bunch of us who go to bed and dream about differential equations but never really communicated them very well finally got around to writing open source simulation engines. So the main one is the virtual brain. If you Google the virtual brain, it's Python based, so it's not just open source, but it's also based on a freeware simulation platform, so it's friends with Russ Poldrack and others. It's rather ambitious, so it's kind of a model that will do everything, and it's got a large community. If you go to SFN, you'll see the virtual brain booth. They have virtual brain nights. They do all sorts of wonderful things, but you really have to invest quite a little bit of time, and you need preferably someone on your team with Python debugging skills. So then Stuart Heitman and I thought, even though MATLAB's a bit of a dirty word, some people still use it, and I use it because I'm that sort of person. You get easy to read scripts and functions. You can write your own stuff. It's free, either if you're at a university or if you know a guy. All you have to do is subscribe, and then you can download it for free, and Stuart is running a very active behind-the-scenes program here. This is what it looks like. you basically just put it in your path. There's very simple, you can do it in 3 minutes, and then you run something I'll show you, and it brings up this GUI, so you can see the equations, the time portraits, the attractors, and then space-time. And you can even get into the integration. Here's the equations, and you can either use, we've got about 20 models, but you can make your own model. And here it is running. Basically, it's so ridiculously easy. You create something called sys. I'll show you how to make that. And then you go GUI equals this thing, bracket sys, and it brings this up with all the default parameters, which you can then move about with sliders. So we see it as a really good platform for people who want to learn what all this gizmo about equations, phase spaces, time series can get their hands on and play around with. And of course you can batch it, and if you've got a supercomputer, you can parallelize it, you can do large-scale simulations, but you can do them more quickly on the TVB in Python. That's all you need. That's all you need to do. Okay, so here's our whole brain dynamics, and then we're going to put them at each different region of the brain, and then we're going to couple them together, and then we're going to do this. This is my connectivity matrix. It's one that we've got from diffusion imaging. We use constrained spherical deconvolution for the diffusion mavens in the room, and then a probabilistic. So we do deconvolution, we don't look at the tensor, and then we use a probabilistic fibre tracking algorithm, and then all sorts of gizmos to get sparsely thresholded matrix. I work a lot with Andrew Zaleski, and he likes deterministic algorithms. So it's a bit like I say potato, he says potato, whatever. And this is what happens. Okay, so you can now do this at home. Beware, if you do it with a time delay on your MATLAB, you'll be able to simulate a few hundred milliseconds, but then it starts chewing up your memory. So these are 6-minute simulations, and these are these beautiful things that come out. This is an example of emergent phenomenon. We didn't put these patterns into the model. All we do is basically have an oscillator in the connectome, and out come all these pretty looking patterns. Applied mathematicians aren't that surprising that in excitable media you get rotating waves, breathers, and travelling waves. But I was certainly happy when we saw them. I've actually presented this 3 years ago at Human Brain Mapping, but we've done a lot of work on them since. You might say, oh, it looks pretty, it's just a bit of a nuance. Well, I say to you, go and read the literature in all these famous journals, and you'll see propagating waves becoming more and more a likely substrate for how the brain may operate. You get, if you're in an experiment, you're doing binocular rivalry, so you're seeing red and green gratings. The percepts transition is a travelling wave. That's this wave, that's this paper. If a primate is about to move its arm, you see a propagating wave across motor cortex of a beta oscillation. You can measure these things in the visual cortex, and you can even see that the primary visual response in visual cortex seems to propagate as a visual wave. And there was a paper just last week in Neuron saying alpha rhythm was a propagating wave. And why? Why do we get these waves? It's quite simple, really. This is our connectome. This is the distance between nodes, and this is the logarithm of the connection weight. So you see, on top of this connectome is this smooth, what we call a kernel. So things that are closely in physical space are more likely to be strongly connected. And that's how you get these waves. But the nature of the waves and the transitions between them is not a trivial prediction from this. Yeah, and it's not just a simple kernel. It's got all this variability, and this is really important. It's called frozen spatial noise, and it determines the velocity. Okay, also at Human Brain Mapping in Honolulu, and that was a lovely meeting. Some good surf nearby. But Terry Sinowski showed this data. This is from humans, ECOG data during epilepsy surgery, and this is sleep spindles. And Dr. Sinowski here, our travelling waves, looking very brain-like. Okay, what happens to the waves? They don't just get stuck, they transition from one to the other to the other. I don't want to go into too much depth here because it gets a little bit obscure. We can use information entropy and partition these, and we get a characteristic timescale. We can also convolve them with a hemodynamic response function and see fluctuations in global efficiency. This is a network measure of connectedness in the whole brain. And of course, you can then go to the Human Connectome project. You can take data and you can do the same thing, measure the global efficiency. And we found our neural mass model was a nice model for these fluctuations or changes in time resolved global efficiency. I might say that this was with Andrew, and there's obviously still a controversy about the role of physiological confounds that Timothy will bring to us, and also the nature of the null model that hasn't been resolved. But these are slow time scales. What about fast time scales? And Maria spoke about a hidden Markov model. So we can partition these and we get a gamma function for our dwell time distributions. And then working with Mark Woolley, we can get people to go and sit, well I didn't, but they did, sit in a MEG machine, do source reconstruction, and then invert a Bayesian model of hidden Markov process. So Maria presented that to you. I guess it's a different version, but they allow switches between discrete networks and find these 7 networks and then look at the visitation times. And then they sent us the data and we looked at the whole distribution and we find qualitative and almost quantitative matching of the dwell time distributions from our model as observed directly in biomagnetic material. Okay, biomagnetic time series recordings. Here's a little bit more that can be done with these waves. Of course they're pretty, but you've got to remember there's got to be an architecture behind them. Dr. Roberts spent several years in a small room with a window. You can do a Hilbert transform on these, and you can look at adjacent nodes, and then you can just find the local vector of the Hilbert transform gradient, just like Vince showed the derivative. This is the Hilbert transform derivative, and so every region of ours in the brain has neighbouring regions, and that will determine a vector. And just almost identical to using a deterministic streamline algorithm, you can then find these streamlines of these waves. And the nice thing is, even as the waves propagate, these vectors in the streamlines stay constant. Waves are just moving like on an elevator around these streamlines. And what we've discovered is that the streamlines have sources and sinks, and when they collide, then that particular wave pattern collapses and you get the little bit of entropy and then you get the next wave. So that's our model-based answer to brain states and dynamic functional connectivity. Of course, I've painted a bit of a pretty picture, and it's not necessarily completely like that. It turns out our waves are propagating too quickly, so we need to look at that, etc., etc. But this is what a movie looks like. Here's the waves, here's the vector field. You can see a couple of sources here, they're quite unstable, and then a nice stable sink here, see that? And so this is the skeleton that's determining the waves, and when this all collides and goes pear-shaped, then you get a new configuration. And this is because the brain, like all thermodynamic engines in the universe, is operating in an energy landscape and seeking local minima, and that's why it reorganises from one state to the other. But anyway, I'm getting prosaic now. That's it. Thank you. Actually, I do have one last slide.
Oh, okay.
Press the wrong button. And then you can read some papers of ours in the toolbox, and possibly there'll be... This is not a book, this is a handbook. It's slightly underwhelming, but it's how to use the toolbox, and maybe there'll be a proper book sometime. Okay, so questions?
We have time for some questions, yeah.
Yes?
So you have your parameter cell task manipulatory parameters, so you put metabolic parameters.
Oh, yes, definitely. Well, we can couple it to the bold response because we know what... You see, the nice thing is about when you model something, you have the ground truth. I mean, it might be erroneous ground truth, but you know what's going on. So there's synaptic currents in our models, and then we don't know in reality how that drives neurovascular coupling, but we can make some assumptions, and we can put the bold model on, you know, like the balloon Wynne-Castle model, or our own version of that, and we can simulate the bold. And so we can go from neural activity to simulated bold, we could go to simulated FTG, simulated flow. But what's also very interesting is, of course, when the brain gets really active, it's not driving around, in my opinion, with a full petrol tank, right? That would be silly. It's kind of just near, it's probably 1/8 full, because you've got the body to continually supply the brain. But what I'm very interested in, or we're very interested in, is that if it gets a little bit too active in a pathological state, you draw down on that metabolic footprint, and then the actual supply of metabolism becomes a slow variable in your model. Is that your question? Okay.
How are you determining the connections? Are they just binary?
No, they're fully weighted. You saw that distance, and that was 5 orders of magnitude. Log weight kind of compresses it. But it's the normalised streamline count. That's slightly old data, but now we're doing all the proper human connectome pipeline, and we're working with MR-Trix to do proper anatomically informed, re-weighted normalised streamline densities. But that's basically the connection strength.
How well do these models do at matching our spectrum for EEG?
Not too bad. The model I showed, chaotic dynamics always give you a 1 on F-like spectrum, which is great because the spectrum's not flat. You get a bit of an alpha rhythm and a bit of a gamma peak. If you really want to fit your model to EEG data, there's other models that do better than that. There's a corticothalamic neural field model that came from Vic Yerser and Peter Robinson, and that gives a brilliant match, not just to the spectrum, but to the co-spectrum. So that's kind of like, we're not, we've got a recipe book of models at the moment. It's quite messy. We should really have, you know, a standard model, but we don't have a standard model.
You introduced 2 packages for the brain dynamics, the virtual brain and the dynamic activity toolbox. Could you tell us what you prefer to do in one versus the other, or why, or both?
Okay. Yes. Let me see if I can get that. Here it goes. I'm too old to know how to use Python and carry all those libraries around. I can use Python and then GitHub and version control. And it's almost like a confession these days. I like MATLAB. I know I'm getting ripped off. I gave a talk at the MATLAB conference. I got a mug, right? For thousands of dollars a year, okay? I just like this. This is me and Stuart wrote it. Stuart's a software engineer. I think the documentation is beautiful, but it's MATLAB based and it's slower. If I really wanted to get serious, I would, well, our group uses the virtual brain. MacShine uses the virtual brain. It's Python based, it's got lots of models, it scales, it runs quickly. I think it's the question you want. Bear in mind, I'm involved in both, so there's disclaimers of conflicts of interest here. I'm not making money out of these, though. I'm paying for these. I'm not paying for this one. Time's up. So says my timer. I think you should, if you're really interested in it, give both a go. There's a big community of users here. If you're a real hacker, coder, get into the virtual brain or do your own toolbox. If you just like MATLAB and you want to learn you want to learn around the concepts, give the Brain Dynamics Toolbox a go. And if it breaks, you can email Stuart Heitman.
Thanks, Mike.